Okay, in the last videos on section 1.1, we were talking about systems of linear equations and how to solve them. And we understand that we have substitution and elimination, which is what we're used to, but now we kind of formalized it into this thing called Gaussian elimination, where we had these operations, which admittedly are the same as the operations you use for elimination. And we used that to solve the systems of equations. We're going to formalize that even more. But in order to do that, first, we need this idea of what's called the matrix. And if you have taken, I think statics, differential equations maybe, different classes, matrices will pop up. Matrices is the plural of matrix. So these things will pop up. They used to actually teach them in high school. I don't really think they do anymore. But the idea of a matrix is just a rectangular array with a bunch of numbers in there. We'll go with 2, 1, 3, 7. And that right there is a matrix. As far as it goes, once you have an idea of a matrix, there's kind of all the notation and terminology that comes along with it. The general form of a matrix would be maybe A11, A12, A21, A22. And these subscripts right here, they should look similar. They're actually the subscripts we use when we're writing out our general form for systems of equations, because that's actually what we're going to use these matrices for. They're going to kind of transfer back and forth. But here, the way this works, obviously we have rows and columns. The first entry right here is the row. So this is the second row, first row, second row. That's the column. So first column, second column. And then in general, we just have an M by N matrix, where M is the number of rows and N is the number of columns. So in this case, this has 2 rows and 2 columns. So it's a 2 by 2 matrix. It's also called a square matrix because it's a square. I don't have to have it that way. I could have 3, 1, 7, 2, 1, 4. Now I have 2 rows and 3 columns. So this is a 2 by 3. 2 rows by 3 columns. And you can even have, just to make it as easy as possible, that's a matrix. That's actually a 1 by 1, which really we just think about as a scalar. But essentially, this is going to give us another way to write out our systems of equations and maybe make it easier to solve them or to understand what's going on. More notational stuff that can pop up. These are called real matrices because all of the entries which have to be numbers are real numbers. But you could have like a complex matrix where you had complex values in there. For the purposes of what we're doing, everything will be real unless for some bizarre reason I arbitrarily say it's complex and throw complex stuff in there. But essentially, all the matrices we use will be real matrices. But we have rows, we have columns, we have square matrices. In terms of the systems of equations and the way we're going to use them, suppose we have this system. 2x1 plus 3x2 equals 4, and 4x1 minus x2 equals 7. So I have a system of linear equations there. I can actually form 2 different matrices from that. First off, I can have what's called the coefficient matrix. For the coefficient matrix, I just use a matrix of all the coefficients in my system. So in this case, 2, 3, 4, -1. I can also have what's called the augmented matrix. here, I do my coefficients, 2, 3, 4, -1. But for this one, I also include the constants on the right, 4 and 7. Sometimes, and your book does not appear to do it, I haven't looked through every problem on every page, but I have not seen your book listed anywhere so far. But some people will actually kind of do a little dot, dot, dot right there. Because essentially you're thinking about them as systems of equations. That's not part of the matrix, but you're thinking about them as a system where these are the variables, these are the constants on the right. So just be aware, if you look in other places, look at other videos, other books, whatever, occasionally people will draw little lines there. But we have a coefficient matrix and an augmented matrix. And just using what we know about Gaussian elimination, we're going to do some examples of stuff like that in a minute. But suppose I have an augmented matrix that looks like this. What are the solutions to my system? Well, here, again, if it helps, I'll draw this. I understand if I just write these as equations, x sub 1 plus 2x sub 2 equals 2, x sub 2 equals 4. And now, x sub 2 is 4, I can plug in there. X sub 1 is equal to 2 times 4 is 8, 2 minus 8 is -6, and I get my solutions easily. So we can see how these matrices will allow us to write out our systems of equations and have a nice systematic way to solve them. This right here is called, to make sure to use your book's notation, row echelon form. And the idea is, again, if I do something like this, where I get a bunch of ones, well then when I think about the system, I immediately get one solution, and then I can kind of back substitute row by row by row and generate all my other solutions to my system. There are actual formal rules, just so we are clear. I will write them out. But, that's still working? Yep, good. Okay. Rules for row echelon form. Any rows containing all zeros are at the bottom. And don't worry, once we have these written down, we'll kind of look at a few. For each row, not all zeros. The first entry is 1, and for two successive rows, the leading one is further to the left on the higher row. So, if I have this matrix right here, 1, 3, 1, 1, 1, 4, and 0, 0, 0. Is that in row echelon form? Sure. In this case, we have a third row there, but it's all zero, so it doesn't really matter. So it just has to go at the bottom to put it in row echelon form. Again, the idea being I want this diagonal of ones. If the matrix looks like this, 131,000,014. That's not in row echelon form, simply because the zeros aren't at the bottom. But again, we know from our ideas about Gaussian elimination, I can just take row 2 and change it with row 3 and rewrite it that way to put it in row echelon form. So essentially, we're going to use our rules for Gaussian elimination to manipulate these matrices to get them in a form that's nice and neat that lets us find our solutions. So let's see. I have an example. There is also one more note on terminology because we're going to use it. There is row echelon form and reduced row echelon form. Just as an example, 1, 0, 0, 3, 1, 0, 2, 4, 1, 1, 3, 7. So suppose I have that matrix after I do all my row operations. Don't worry, we're going to do some row operations in a minute. But suppose I have that matrix. Is it in row echelon form? Well, sure. I have this diagonal of 1s right here, and I can read off, just thinking about the system, x sub 3 is equal to 7. X sub 2 plus 4x sub 3 is equal to 3, so I can solve that. X sub 1 is 3x sub 2 plus 2x sub 3 equals 1. Backward substitute, solve that, and I can get the solution to my system. So we're in row echelon form. Reduced row echelon form, any column that has a leading 1 in it has zeros everywhere else. The idea being, before we even write it, right here, like I had said, if I wrote this out, I could say x sub 3 is 7, x sub 2 plus 4x sub 3 is equal to 3, x sub 1 plus 3x sub 2 plus 2x sub 3 is equal to 1. And then I get this one, I plug it in here, backward substitute, get that, plug both of them in here, backward substitute, get that, and then I'm done, which is fine. In reduced row echelon form, and I'm just going to make these up, I just made this one up on the top of my head, but it would look something like this. There's a leading 1 here, so all other entries are 0. There's a leading 1 here, so all other entries are 0. And again, these ones I'm just making up. But now, if I have it in this form, x sub 3 is equal to 3, x sub 2 is equal to 2, x sub 1 is equal to 1, and I get my solutions immediately because all of these are 0, so I don't have to worry about the backward substitution. So sometimes when we solve these, we will put them in row echelon form like this, and then backward substitute and solve. Other times we'll put them in reduced row echelon form, and then we won't have to backward substitute, we'll get our answers immediately. So make sure when going through your homework and exams and all of that, make sure you understand what the question is asking and you put your answers in the correct form. We have matrices, we have coefficient matrices and augmented matrices. Now we have row echelon form matrices and reduced row echelon form matrices. Make sure you understand what's being asked so that you can get the correct answer. And let's see. I think before we end this video, we're actually going to do some row operations to see them written out and to see the form we need to write them in. We kind of did it on the other videos, so we'll expand on it even more. And then I'll make another video going over even more stuff that we need. So suppose we have this. x sub 2 plus x sub 3 minus 2x sub 4 equals negative 3. X sub 1 plus 2x sub 2 minus x sub 3 is equal to 2. 2x sub 1 plus 4x sub 2 plus x sub 3 minus 3x sub 4 equals negative 2. And x sub 1 minus 4x sub 2 minus 7x sub 3 minus x sub 4 is equal to negative 19. So we have 4 equations, 4 unknowns, x sub 1 through x sub 4. And I would point out, using substitution and elimination that you know from high school, could you solve this out? Yes, you could. Would you actually want to? Just looking at it, it's like, okay, so what should I substitute for first? I don't know, maybe the first one for x sub 2 and kind of go from there, hopefully. I don't really know. Maybe the second one for x sub 1 because it's first, or I don't really know. And that's the point. And even with elimination, you're kind of stuck with, okay, good Lord, what am I going to eliminate and how am I going to write this and how's this going to work? Using matrices, we get a nice formal way to do it that structures everything and tells us what to do. So, if I write this out in matrix form, keep in mind the first entry here will be 0 because there's no x sub 1. Then it'll be 1, 1, negative 2, negative 3. 1, 2, negative 1, 0, 2. 2, 4, 1, negative 3, negative 2, 1, negative 4, negative 7, negative 1, negative 19. And for my benefit, I'll put the little dot, dot, dot there so I know it's augmented. Now I want to manipulate this using my row operations, my Gaussian operations. First off, I know I want x sub 1, my leading term in the top left, to be 1. So first, I'm actually just going to flip these two, R1 and R2. And the way we write that, R sub 1, double arrow, R sub 2, which just means flip them. So if I rewrite it, now I get, I'm quickly going to run out of room on this small board, but 1, 2, negative 1, 0, 2, 0, 1, 1, negative 2, negative 3, 2, 4, 1, negative 3, negative 2, 1, negative 4, negative 7, negative 1, negative 19. Now I have my leading one here, and I actually already have a 0 here. So now I want to start removing those. So first off, I'm going to do R sub 3 plus negative 2 times R sub 1 into R sub 3. And again, to kind of get the notation down, I'm going to take my third row right here. I'm going to combine it with negative 2 times the first row, because then I'll get negative 2 plus 2 here, which will make this 0. And once I do this, I'm going to rewrite that and replace the third row with my new answer. So that's kind of how this works. All of this is going to take the place of that. So now, the first two will stay the same, so will the fourth. Now, negative 2 times the fourth times the first plus the third. Negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times 2 is negative 4 plus 4, 0. Negative 2 times negative 1 is 2 plus 1, 2. Negative 2 times 2 is 0 minus 3 is minus 3. Negative 2 times 2 is negative 4 plus negative 2 is negative 6. And then the bottom stays the same. 1, negative 4, negative 7, negative 1, negative 19. Now, I need to get rid of this. So I'm going to do R4 plus negative 1 times R1 into R4. And I get, now the first three stay the same. 1, 2, negative 1, 0, 2. 0, 1, 1, negative 2, negative 3, 0, 0, 2, negative 3, negative 6. Now here, negative 1 times 1 is negative 1 plus 1, 0. Negative 1 times 2 is negative 2 minus 4, which is negative 6. Negative 1 times negative 1 is 1 minus 7, which is negative 6. Negative 1 times 0 is 0 minus 1, negative 1. Negative 1 times 2 is negative 2 minus 19, which is negative 21. And now, sadly, I'm out of room. So I'm going to have to go over to the left and start erasing. And we'll switch back. This is the good black one, right? Good. Okay. So now I have a leading one here. These are all zeros. I have a leading one here. So I need to get rid of the 2 and the negative 6. I'm sorry. We're going for echelon form, not reduced row echelon form. So I can leave the 2. I just need everything below the 1 to be 0. So I need to get rid of the negative 6. Which means I'm going to do r sub 4 plus negative 6 times r sub 2 and put that in r sub 4. So again, the first three rows stay the same. 1, 2, negative 1, 0, 2, 0, 1, 1, negative 2, negative 3, 0, 0, 2, negative 3, negative 6. And now for the last row, what am I looking at here? R sub 2, okay. Negative 6 times 0 is 0, plus 0 is 0. Negative 6 times 1, well actually my bad, I need positive 6, because that's already a negative 6. 6 times 0 won't change anything. 6 times 1 is 6, 6 minus 6 is 0. 6 times 1 is 6, 6 minus 6 is 0. 6 times negative 2 is negative 12. Negative 12 minus 1 is negative 13. 6 times negative 3 is negative 18. Minus 21 is negative 39. Now, I need to get a 1 here. And I need to get a 1 here, and then I'll be good. So we'll start here. In this case, I can just take r sub 3 times a half and put that in r sub 3. So now, here, just to maybe save a little space on the board, we're going to do that. But I know that will make this a 1, and this row will be good. So now I'm going to do 2 and 1. This row needs to be multiplied by negative 1/13. R sub 4 into r sub 4. Since I'm not manipulating the rows and combining one row with another, I'm dealing with 2 separate rows. I'm going to do them at the same time. And this is still running? Yes, good. Okay, so the top 2 rows will stay the same. 1, 2, negative 1, 0, 2, 0, 1, 1, negative 2, negative 3. Now we do half of R3 into R3. So I get 0, 0. 2 times a half is 1. Negative 3 times a half is negative 3 halves. Negative 6 times a half is negative 3. Bottom row, 0, 0, 0. Negative 13 times negative 1 over 13 is positive 1. Negative 13 times negative 39 is positive 3. Now I have it in row echelon form. Now I can read off my answers if I want to. X sub 1 plus 2x sub 2 minus x sub 3 is equal to 2. X sub 2 plus x sub 3 minus 2x sub 4 is equal to negative 3. X sub 3 minus 3 halves x sub 4 is equal to negative 3. And x sub 4 is equal to 3. And now, given how long this video is, I'm going to stop right there. But there's x sub 4. Plug it in there, I can get x sub 3. Then plug x sub 4 and x sub 3 in here, and I get x sub 2. Plug x sub 3 and x sub 2 in there, and I get x sub 1. And I can actually get my solution. And I actually did this separately. X sub 1 should be negative 1. X sub 2 should be 2. X sub 3 should be 1. And x sub 4 should be 3, which it actually is. Problem here, looking at it really quickly, 3 halves times 3 is 9 halves. That one's not going to work. So now we get to see where I made one algebra mistake. Using row sub 3. And it's probably on the one I erased. Anyway, clearly I made an algebra mistake somewhere because this is the actual solution. And if I plug in x sub 4 right here, I'm not going to get x sub 3 is equal to 1, which means somewhere in there I made one algebra mistake amidst all the numbers. So feel free to go back through every single line and try to figure out where it actually is. Oh, wait a minute. I think I just found it. Negative 2 times r sub 1. 2 plus 1 is 3. This should be a 3 right here. Right here, negative 2 times r sub 1. Negative 2 times negative 1 is 2. 2 plus 1 is 3. This will stay the same. None of these other ones. I will point out, one of the nice things about writing your row operations like this, you can tell which operations don't affect the row you care about. That has to be a 3, which makes this a 3, which means I don't multiply by a half, I multiply by a third. Now, 3 times a third is 1. Negative 3 times a third is negative 1. Negative 6 times a third is negative 2. And now we check ourselves. X sub 3 minus 2x sub 4 is equal to negative 2. And yeah. I'm reading this backwards. X sub 3 minus x sub 4 is equal to negative 2. X sub 4 is 3. 1 minus 3 is negative 2. And there we go. And again, I do stress, while that seems a little cumbersome and I get to the end, and in theory, from your perspective, you wouldn't know the answer going in. I had already solved this out separately on my own. But if this was substitution or elimination, you end up with pages and pages of scribble, and if you somehow end up with a mistake, you have to go back through all the pages and say, okay, good Lord, what did I mess up, or do I have to start all over, or what? Here, because we have these nice row operations listed out and organized, like I said, I knew there was an issue with r sub 3, so I didn't even bother looking at these two, because the operations didn't involve r sub 3. The mistake had to be on one of the ones with an r sub 3 in it. So there are benefits to using these matrix operations. They keep everything neat and organized. Like I said, this video is long enough now, so I'm going to end it now and make another video doing even more matrix stuff that we need to know.